So here's a crazy question for you. Can an AI actually weigh an entire field of plants just by looking at a photo? I mean, it sounds like something straight out of science fiction, right? But that's exactly the experiment we're going to dive into today. We're going to walk through how you can teach a computer to do just that. So what's the big deal here? Well, think about it. The way we do this now is pretty old school. You have to physically go out into a field, cut samples of the plants, take them back, dry them out, and then weigh them. It works, for sure, but man, is it slow and a ton of work. The big question is, can we just skip all that? Can we replace all that manual labor with a smart algorithm and a camera? Okay, so here's how we're going to tackle this. First, we'll lay out the challenge itself. Then we'll get our data ingredients ready. After that, we'll build a few different models, pit them against each other in a kind of bake-off, and finally, we'll analyze the results to see who came out on top. All right, first things first. Let's really dig into this challenge. How in the world do we get from the pixels in a picture to an actual tangible weight in pounds, or in this case, grams? So what are we asking our AI to do exactly? It's not just one number we're after. From a single photo, we need it to predict 5 different things: the dry weight of the green stuff, the dry weight of the dead stuff, and the dry weight of any clover in the shot. Plus, it needs to figure out a specific metric called green dry matter, and then of course, the total dry weight of everything combined. You know, any AI is only as good as the data it's fed. And that brings us to our next crucial step, preparing the ingredients. This is all the behind-the-scenes work that honestly makes or breaks the whole project. Think of our data prep like a recipe with 4 key steps. First, we load up all our images and measurements. Second, and this is super important, we split our data. 80% is for training, that's what the model learns from. The other 20% is for validation, that's our test. Third, we standardize our target values, which I'll explain in a sec. And finally, we create these things called data loaders, which are basically like little conveyor belts that feed the data to our AI in nice, neat batches. So you might be wondering, what's this standardizing thing all about? We use something called a standard scaler. All it does is take our different weight measurements and squish them all onto the same scale so they have an average of 0. Why do this? Well, it stops the model from getting biased and thinking that a big number is automatically more important than a small one. It helps it focus on the real patterns. Okay, our data ingredients are prepped and ready to go. Now it's time to design the chef, so to speak. This part is all about building the actual AI model and setting up our experiment, our bake-off. The tool for this job is something called a convolutional neural network, or CNN for short. You can just think of it as an AI that specializes in vision. It's built from the ground up to find patterns in images, which, makes it absolutely perfect for what we're trying to do. Here's a secret about machine learning, though. You almost never get it right on the first try. You can't just build one model, cross your fingers, and hope it works. The only real way to find the best approach is to run an experiment and test a few different ideas against each other. So, what's the big variable we're testing? It all comes down to something called model depth. We're basically going to build a few versions of our CNN, and each one will have a different number of these internal processing blocks. The big question is, does making the model deeper, or more complex, actually make it better? All right, let's meet the contenders in this bake-off. We've got 4 of them. Model A is our simplest, with just 2 of those processing blocks. Then we have Model B with 3, Model C with 4, and finally, the deepest and most complex one, Model D, with a full 5 blocks. Let's see how they stack up. Okay, the stage is set. The competitors are ready. It's time to run the bake-off. This is where we actually train these models and see which one can learn the job best. So how does the training actually work? We're going to put each model through 20 rounds of training, or what we call epochs. An epoch is just one full pass through all the training data. At first, the models learn really fast. As they go on, you start to see some patterns emerge, and by the time we hit that final 20th lap, the training is all done. But how do we know who's winning? We need a scoreboard, right? We're going to use 2 main scores. The first is called loss. That one's easy. It's just a measure of error. The lower the number, the better the model is doing. The second is the weighted R-squared score. That one tells us how well the model's predictions match up with reality. For that score, higher is better. A perfect score is 1. A score of 0 basically means your model is no better than just randomly guessing. And that's a wrap. The training is done, the numbers are crunched. Let's get to the good part, analyzing the final results. Let's see which of our models actually won this bake-off. Whoa. Okay, let's take a look at what happened here. On the left, you've got that R-squared score. Higher is better. On the right, you've got loss, or error. Lower is better. Now look closely. Two of those lines, for our simpler models, are pretty stable. They're learning consistently. But then, look at the other two, the ones from our deeper, more complex models. They are jumping all over the place. That is a huge red flag for instability. And if the charts weren't clear enough, this table spells it out in black and white. Just look at that R-squared column. The 2-block model is our winner, hands down. The 3-block is right behind it. But look at the 4 and 5-block models. Their scores are negative. Remember what that means? A negative score means the model was actually worse than if you had just guessed the average weight for every single photo. It completely and totally failed. So the verdict is in, and it's a knockout. The simpler models, with just 2 and 3 blocks, trained way more stably and gave us much better results. The deeper models were a total mess, unstable, erratic, and their performance was terrible. This is a textbook example of something called overfitting. The complex models were too smart for their own good. Instead of learning the real pattern, they just started memorizing random details and noise in the training images, which made them useless on the test data. This bar chart just drives the point home perfectly. Look at the positive bars for the 2 and 3-block models. Now look at the disastrous negative bar for the 4-block model. The simpler models clearly won. The complex ones weren't just a little worse, they were a total disaster. So after all that, what's the one big lesson here? It's simple, really. Bigger isn't always better. At least for this problem, making the model deeper and more complex didn't help at all. In fact, it made things significantly worse. Simpler was better. Now, even though we found a winner, let's be real, the score isn't perfect. There's still a ton of room to get better. Which brings us to the final big question. Where do we go from here? What's the next experiment? Do we need more data? Should we tweak the training settings? Or maybe try a completely different kind of model? And that's really the fun of it all. There's always another question to ask and another experiment to run.